Welcome everybody to our August edition of the AEP webinar hosted by Sickle Cell Anemia Awareness of San Francisco. I have two people speaking today. One is Ted Love, the other is Kobe Dufu, and now it is time for you guys to take the mic. Presentation is yours, fellas.
Okay, Antoine and Nadina, thank you both for inviting us today. Just by way of background, I'm Ted Love. I'm a cardiologist and scientist by training. I was invited about 9 years ago now to help build a company from a very early stage idea that we thought could be transformative for sickle cell disease. Because of my personal background, particularly as an African American, I thought it was important. So I actually came out of retirement to do this. Today, the presentation is really going to be led by Kobe Dufu, who's going to introduce himself next. But I'll just say that Kobe is one of the major reasons that I agreed to come out of retirement. This was a decision that was based upon really my scientific belief that we could do something truly transformative for sickle cell disease. And Kobe was one of the key scientists in generating the data to convince me that we had something very important on our hands, assuming that we could build a company, raise the money, and do other things. So with that, I'll turn it over to Kobe.
Thank you, Ted. My name is Kobe Dufu. I'm originally from Ghana in West Africa. Growing up, I had family with sickle cell disease. When my interest in science peaked and I had the opportunity to immigrate to the US, pursuing my graduate studies at Harvard and getting some really great training, I had an opportunity, as Ted mentioned, 9 to 10 years ago, to join a company that was all of a sudden focused on sickle cell disease. Imagine how excited I was, finally having the opportunity to work on a disease that actually affects family members. And with that, I took upon that opportunity, moved from Boston to San Francisco, and the rest is history. So without further ado, today's story is going to be about sickle cell. And if I can project the slides. The title of today's talk is an approach, a rational approach to conquer sickle cell disease with a small molecule in a pill. Now, this slide you're looking at, so this slide you're looking at is basically what we call a blood smear, and it's just a fancy term for taking blood from a patient or an individual and putting it on a slide and then looking at it, staining the cells that are within blood. Now, typically red blood cells are supposed to be round, as you can see, but without obviously pointing you to it, you can also see that in addition to the round cells that are present, that you have these sickle-shaped cells that are within the blood of this particular individual. Now, the blood came from a patient who has sickle cell disease, which is why within that blood, you will find sickle cells as part of normal cells that are also circulating in the blood. Now, if this doesn't make sense to you, my hope is that after today's presentation, that you understand why these cells are there and how they contribute to disease, and what we've taken as part of GBT's effort to provide a therapeutic that can address this. So, because I'm sure the audience is coming from a place with different backgrounds, I just wanted to visit some basic biological concepts so that we can all be aligned. And also, I can give you guys the opportunity to really take something from this presentation. So cells are really the building blocks, if you think of it, of human beings. The same way you use bricks to build a house, you consider cells as building blocks. Now, within each cell is something called DNA. DNA is just a fancy term for an entity that exists within the cell that carries the information that makes all of the proteins, which I refer to as molecular machines within the body. If you consider the cell as a factory, the employees who are at that factory are the proteins, and they each do different things. So if you consider, for example, a packaging factory, there are people that make boxes, there are people that make labels, et cetera, et cetera. Now, these people each represent what we call proteins in the human body. I hope that makes sense. So proteins have different functions, and one of the most important proteins that we're going to talk about today is called hemoglobin. And hemoglobin's function is to carry oxygen throughout the body. Now, we are organisms that definitely need and depend on oxygen to survive. We take in oxygen, and we use that oxygen to generate energy, which we use to power our cells so that we can function throughout. Now, every now and then, something happens called a mutation, a change in the DNA sequence, which unfortunately can cause disease, because changes in the DNA sequence leads to making proteins that are no longer sometimes functional, or they achieve different functionality. They get to do something extra than what they're designed to do. Okay, so in sticking with hemoglobin and its function, in sickle cell disease, a mutation has occurred in the gene that provides the protein called hemoglobin. Now, normal hemoglobin from a healthy person is called hemoglobin A, whereas because of the sickle mutation, the protein that comes out, which is supposed to be normal, is now called sickle hemoglobin. The other concept that I want to throw out there is that for a person to have sickle cell disease, they must get at least one copy of the gene that has the mutation from dad, and at least one copy of the gene that has the mutation from mom. That as mom and dad come together, their progeny, the kids that have sickle cell disease must carry both copies of the S gene to have sickle cell disease. So in this example, what we call a Punnett square, both parents have sickle cell trait because they carry only one copy of the S gene. Now, when you put them together, there are only 4 possible combinations. When you have both S genes, you have sickle cell disease. When you have only one copy, you have what's called sickle cell trait. If you don't have any S genes, then you basically have a normal phenotype. Interestingly, the AA phenotype is benign, meaning that you don't have any sickle cell disease because you don't have sickle protein, right? But the AS phenotype means you have some sickle protein, but you also have some normal protein present. And because you have some normal protein present, it masks the effect of the sickle hemoglobin, and therefore, for the most part, in the adult life of a sickle cell trait individual, they actually are asymptomatic. That's a fancy term to say that they don't show some of the clinical phenotypes of sickle cell disease. So with this, I hope we're all aligned on the background, and I can now move into sickle cell. So sickle cell disease, how many lives are impacted? Now, in the U.S., there is, at least among the African American population, the rate of incidence of sickle cell disease is about 1 birth in every 360 newborns that are born among the African American population. And this comes to about 100,000, roughly 100,000 patients within the U.S. In the U.S., and by terminology, that will be considered a rare disease. Anytime you have a disease that affects less than 200 people, it's a descriptive term that's used. It's called a rare disease. But of course, sickle cell is not a rare disease, because if you go globally, there are millions of people who have sickle cell disease. And I'd like to draw your attention to where I'm from in Ghana, which is shown on this African map. You can see from this heat map, the redder it is, the more people are. You can see that most of the patients are located in Africa, and most of the people that have sickle cell disease come from parents of African descent. So the occurrence of sickle cell disease in West Africa is about 300, 400,000. In fact, this was 2010. I think the latest estimate is more around 500,000 new births per year. And that translates to millions of people in Africa having sickle cell disease. What's interesting is that malaria actually has something to do with it. And I'll be very brief with it because I don't want to go into the science of it. It turned out a long time ago that you were more susceptible to die from malaria than you were when you had sickle cell disease. Now, when you caught malaria, you died, which meant that obviously you wouldn't contribute to the population. When you had sickle cell disease and you had malaria on top of it, you will also succumb to malaria because you're already anemic, and I'll talk about that later. You're already sick, so catching malaria also led to a death. However, what's interesting is that when you had sickle cell trait, which I just explained to you, that your disease course after catching malaria was much, much more milder, and there's a reason for that. The parasite that causes malaria needs to have what's called a viable red blood cell, a healthy red blood cell, to be able to propagate, to be able to mount a response that causes malaria within the body. But because sickle cell trait was protective, you can see how, if we go back for a second, you can see how if these are protective and you get and AA is normal when you get malaria, AA dies, and SS, because they're already sick, when they get malaria, they also die. You can see that in the population, that most of the folks that remain a while back are individuals that have sickle cell trait. So I hope you can see how having sickle cell trait be slightly protected, that the propagation of the S gene expanded significantly in a place like West Africa. Okay, so what does sickle cell look like in terms of a clinical phenotype? And by the way, I will give you an opportunity to ask questions very soon. So, but you can always stop me if you have a burning question. Okay, so there are two different classes of what we call manifestations in sickle cell disease. It's just basically saying clinical complications, right? There are acute clinical complications, which means, complications that occur that send you to the hospital. Now, some of the acute complications include pain events, so I'm sure if you know about sickle cell, you know about sickle cell pain. And the way one of my cousins describes it is that it feels like needles in her bones. I mean, I can only imagine what that must feel like. Another acute symptom is what we call acute chest syndrome, when you have a massive inflammatory response and clogging of the piping within the lungs. And that actually is one of the leading causes of death in patients with sickle cell disease. Additionally, we have something called strokes, which is because sickle cell disease impacts blood flow in organs such as the brain. When you deprive, importantly, oxygen to some of these regions within the brain, what happens is that because the brain controls a lot of the functions in your motility, you can catch a stroke, and that can lead to losing motion. Actually, also that can lead to some cell death within the brain itself, which, as you can imagine, is not good. We also have what's called chronic manifestations. And if you imagine how sickle cell disease is manifested, and you learn more about it as I talk about it, if you can't distribute oxygen to all of the organs that are within the body, which I mentioned is very important for our survival, then if blood is not reaching some of these organs, you can understand that over time, all of those organs are affected. Basically, if they're deprived of oxygen, then slowly they will die, if you think about it, right? So no organ system is spared. The eyes, the lungs, bones, kidneys, your skin, liver, brain, every organ system that receives oxygen from blood flow has the propensity to be affected by sickle cell disease because of something I'll talk about, right? Because of the lack of oxygen arriving at the tissue. So the chronic manifestations are largely around organ damage, which ultimately leads to death. I mean, if your liver stops working, you are going to unfortunately die. So that's how clinically sickle cell disease looks like. Okay. All right. So now, before I dive deep into mechanistically why you have sickle cell disease, I think it's important to introduce red blood cells and hemoglobin and what they do within the body. Right. Now, human beings are very heavily dependent on oxygen utility. It's very, very important. So when you breathe in, as we did this morning, the breathing exercise we did, you pull in air into your lungs, which contains oxygen. Now, the oxygen, imagine if we didn't have cells called red blood cells that carry this oxygen. If we didn't have it, if our blood was just fluid, oxygen would just have to diffuse and dissolve in a liquid, right? When oxygen dissolves in liquid, it's not at a very high concentration. So very little oxygen can dissolve in liquid alone. Now, nature has designed it so that we have these things called red blood cells that are within our blood. Now, within the red blood cells, within red blood cells, you have proteins called hemoglobin that bind to oxygen, right? So by picking up the oxygen in the lungs, they move through different piping, so your arteries and your veins, to deliver oxygen to your tissues. This is a very, I hope, simplistic diagram. As you can see, oxygen is picked up by red blood cells. It's delivered to your organs. And when oxygen is utilized by your organs to generate energy, one of the byproducts is called CO2, carbon dioxide. The red blood cells then carry that back to your lungs, and that comes out. So this process is very important. It has to continue to ensure that your organs receive the needed oxygen. All right. Now, for this to happen and to be optimal, two very important properties of red blood cells must be considered. The first is that because you have different sizes in terms of arteries and veins in your body, sometimes red blood cells, based on their size, And depending on where they're flowing, if you look at this blood vessel here, the diameter, so the space is so much bigger than the size of red blood cell. So it can flow freely. But when it gets to places, junctions where they're tighter, where the vessels are much smaller, that red blood cell must be flexible enough to stretch, okay, to be able to squeeze through so that it can move forward. That property is called deformability, but for the purpose of this talk, let's just call it flexibility, right? So red blood cells have to be flexible. Also, to be able to carry a lot of oxygen, we need a lot of red blood cells. And what we do have in blood is we've got millions and millions and millions of red blood cells. Not just that, there is more of an amplifying effect. On top of the millions of red blood cells, each red blood cell also has millions, in fact, over 250 million molecules of hemoglobin that consistently I've been talking about. And therefore, because you have millions of hemoglobin molecules, you can carry a lot more oxygen. It doesn't end there. When you look closely, when you actually look at hemoglobin and its structure, it's got 4 different identical repeats that are put together. Interestingly, each repeat carries 1 diatom of oxygen, so it can carry 1 oxygen molecule. So not only do you have millions of red blood cells, and each having millions of hemoglobin, but each hemoglobin molecule actually can carry 4 diatoms of oxygen, which is remarkable. You know, nature is really, really slick in that perspective, right? So you can see how red blood cells can carry a lot of oxygen, right, within the body. And it's a very defined function for that cell. Now, one concept to understand and to that can help you understand, basically how sickle cell disease manifests is the structure of hemoglobin. So hemoglobin looks different when it's bound to its oxygen, right? Now, when oxygen comes off, normal hemoglobin exposes only 1 sticky patch. The proteins are machines, and they have to change to be able to function, right? So normal hemoglobin exposes only 1 sticky patch. Now, with 1 sticky patch, you can get a lot of multiple. Remember, you have millions of hemoglobin molecules. They can't stick to form what we call polymers, which I am coming to. Now, with sickle hemoglobin or hemoglobin S, the hemoglobin, when oxygen bound, is actually fairly normal. There isn't really a big difference in terms of structure. So, a sickle cell patient has no problem picking up oxygen in the lungs, right, and actually delivering that oxygen, right? There are some nuances here and there, but for all purposes, there isn't a big difference. However, when oxygen comes off, instead of revealing on 1 patch, multiple sticky pouches are exposed. Now, this is because of the mutation that I talked to you about. Remember the change in the DNA that I talked about. Now, because they have multiple sticky pouches, now you consider a cell that has millions of these. If you have multiple sticky pouches, the sticky pouches on sickle hemoglobin is such that you can now enjoin multiple units of these deoxygenated hemoglobin molecules. So hemoglobin molecules without oxygen bound to it. They form these long polymers, and I took the liberty of actually showing you how they look like. So this is an electron micrograph, actually looking at how polymers are. Consider red blood cells, for example, as a balloon that's blown, a birthday balloon that's blown, that's filled with sand. Each grain of sand will represent a hemoglobin molecule. When you have that balloon with sand, you can change the shape of that balloon. You can stretch it out because the sand molecules just can move. You can stretch, the balloon into a very elongated shape, right? Because it contains sand. But imagine now taking the sand out and putting in rods. If you put rods into a balloon, you can only assume the shape of that balloon, right? And it's also going to be very rigid because you've got rods in there. Now it's no longer flexible. Now, because you also have rods, remember, rod can poke right through a balloon. That balloon can also burst. That's really what's happening. So these are the rods. This is why you have the sickle cell shape, okay? I took the liberty of putting these videos together, which we've used to nauseam. What I'd like for you to do and to also remember is how hemoglobin behaves. So when there's oxygen around, remember, when there's oxygen around, sickle hemoglobin acts very normally, right? But when you take oxygen away, all of a sudden, you reveal these sticky patches on sickle hemoglobin such that they form polymers. So I'm going to show you a video. This is what a normal red blood cell looks like. This already contains a little polymer. So you don't focus on that, but focus on these 2 cells. These 2 cells are by all measure normal, right? So let's see what happens when we take the red blood cell and then we take the oxygen out of it. You can see how dramatic the change is. You see how dramatic the change is? You went from a balloon that contained sand molecules that don't stick together to a balloon that now contains rods. So because there are rods in there, the cell changes completely, right? It becomes less flexible because you've got rods in there, and potentially the rods can also poke through those cells and release the material. So this happens in the body of a sickle cell patient very often, because when the red blood cells picks up oxygen in the lungs, okay, as it goes through the tissues and releases oxygen, there's very little oxygen. The oxygen is utilized by the organ, right? So what happens is that the sticky hemoglobins polymerize, and this is what happens. Now, some of those cells are able to come back. So what happens when you take these cells and now you introduce oxygen back to them? You'll see what happens in this next video. So these are sickled cells. They contain rods, but when you introduce oxygen to them, voila, they come right back to their round circular shape. It's truly remarkable. The first time I saw that, it was so mind-blowing. I didn't know what to do with myself, right? You can imagine how amazing this is. So the key question for our company is, how can we design a small molecule drug that can control a sickle hemoglobin so that the process of going from the oxygenated state, which won't stick together, to the deoxygenated state, which will stick together, is regulated by this small molecule? To recapitulate how oxygen, the effect that oxygen has on these cells. I hope that makes sense. Okay, so to revisit the sickle cell disease cascade, typically oxygenated red blood cells, you've got hemoglobin that's depicted by these yellow little things that I have in here, right? So the cell is round. It's like a balloon filled with sand. Remember, you can change the shape. It's flexible, all of that great stuff. Now, when oxygen comes off, remember that because of the sticky patches on sickle hemoglobin, they form polymers. And what happens is that you now have the sickle cell shape, right? Now, you can have other different types of shape depending on the rate at which they stick together. But classically, you get this sickle cell shape. That sickle cell shape, remember, is synonymous with balloon with rods. What happens when you put rods in the balloon that are sharp? They can poke right through that balloon. What we call that hemolysis. That balloon explodes. And this is really bad because now it's releasing not just hemoglobin into your bloodstream, but all of the other proteins that are different machines that are not supposed to be in your bloodstream are now circulating in your bloodstream. An important thing is that because the cells are exploding, your body can't keep up with making new red blood cells. You end up in a state called an anemic state. It's just a fancy term to say that your level of hemoglobin has gone down. The amount of oxygen you can carry in your body actually has reduced significantly. That's what anemia means, which is why sickle cell patients fatigue very easily, right? Because they're not carrying as much oxygen as they can in their body. The other thing that polymerization or the stickiness of the sickle hemoglobin does within red blood cells, it makes the cells rigid. As I mentioned, blood vessels are of different sizes. You can see how suddenly having an inflexible red blood cell can block blood flow within the body to a very important organ in a process called vaso-occlusion, which is just a fancy term to say that you've now blocked a blood vessel to, say, the eye, and all of a sudden the eye isn't receiving oxygen. The eye is going to die. It's as simple as that if that persists, right? So those are the two main things that describe what's happening with sickle cell. And that leads to both pain crises, right? You've got a lot of pain in your body, and a progressive organ damage, which over time, if you start losing organs, can lead to death. So I hope that really made a lot of sense.
Kobe,
yes.
Quick question. I wanted to ask if we got a table for a later time, please let me know. I wanted to just quickly ask this question about the beginning of the presentation. There's an idea around sickle cell that is really fascinating for a lot of people to understand geographically how this works or how it spreads or how other ethnicities that weren't a part of the African continent could accumulate this disease within their community. So my question is, and if I can try to do it as in like the simplest way possible, when you talked about the geography around Africa and what was in malaria, how does this create different types? I mean, if it's too long of an answer, then I understand it. But we have just a fundamental basis of sickling process, but then there's different types of sickle cell anemia, right. And then there's different geographies where these types are located at. How is that created? Or
So
how does that happen?
no problem. Great question. And I'm glad you asked that question. And I'll be brief about it because we probably have another entire discussion around that.
Sure,
Right?
sure.
So as I mentioned, the mutation, the change actually appeared in West Africa, right? Initially in Africa, to be precise. Now, as I also mentioned, you need 2 copies of that change, right? To then have a patient that has sickle cell disease. So for the S gene to be propagated, right, in terms of leaving Africa, an African or man or a person of color would have had to have moved to a different area carrying at least 1 copy of that gene, which they can.
Really quickly, would you be able to go back to that slide, the geographic slide?
Yeah.
That'd be
Yes.
great.
Yeah.
Thank you, sir. I appreciate it.
No problem at all. So this is the slide, right? So basically, the mutation occurred in Africa, and as I mentioned, through selection, it accumulated in Africa because if you had, again, sickle cell trait, you're protected, right? If you didn't carry the S gene, you succumb to malaria, right? You needed 2 copies of it to have sickle cell disease. And because you're already sick and you got malaria, you also unfortunately succumb to malaria. So those that existed within the population through natural selection were trait individuals. But having trait individuals means you're creating more of these all the time. Every time a father and mom comes together, the progeny has this distribution, right? Now, someone carrying the S gene might have left Africa to a different geographic region, carrying that mutation on their genes, right? And so by meeting someone who's AA from a different background, marrying children, now the kids will have the S gene, right? Now, if they continue to create individuals that have 1 copy of it, if these come together, certainly they are going to now produce a patient with sickle cell because you get 1 copy of the gene from each parent, if that makes sense. So that's how the propagation has occurred. But you can see how Europeans initially did not have this mutation, right? So you can see that there's a dilution effect, whereas in Africa, as I said, because of the selection with malaria, you had more people that had, that ended up getting sickle cell trait and also had sickle cell.
Gotcha.
And you can also imagine.
Maybe I'll add one thing maybe to help.
Okay.
And so another way to think about Antoine is slave trade. So we went over in the US, we brought in a bunch of slaves from Africa. And many of those slaves had either sickle cell disease or sickle trait. And once that gets introduced into the population, it doesn't go anywhere. In fact, even if, let's say, I'm a descendant of a slave, of course, and I had sickle trait, and I marry a Chinese woman, my kids are likely 50% gonna get one of those sickle genes. If they marry, let's say, a Chinese guy, that gene is likely to stick around. And so you end up with people completely unaffected by their skin color having the gene. So it's a genetic disorder. It's not really a racial disorder, but because of the propagation mechanics, you can see it's more concentrated the closer you are to the African heritage. I don't know if that helps, but
excellent.
That's the way to think about it.
Yeah, I'm in that situation currently right now.
Yeah. Yep.
Okay, I have a question, but it relates to, when we talk about sickle cell, I always knew that it was sickle cell anemia. Okay, much later, it was sickle cell disease. Now, my family or my mom and dad said that I was anemic. So what I'm trying to figure out here is, because they didn't get the information or it hadn't progressed or what have you. But so I have the trait. So that's what I had.
Yeah.
How does anemia and sickle cell anemia, how is that different? How does it differ? I know it's different, but how does that? I don't understand, because they just always said I was anemic. But then once I was pregnant, they found out I had the trait, so on and so on.
Right. Well, your anemia has nothing to do with your trait. A lot of people without sickle trait have anemia.
Right.
And they can occur together. So your sickle trait and your anemia have nothing to do with each other. The name changed nomenclature. What happened basically in medicine is we said sickle cell is much more than just anemia. Sickle cell brings the organ failure, all the stuff that Kobe described. So we decided that it wasn't a good idea to just call it sickle cell anemia. It's a disease that's having a much bigger effect beyond anemia. So sickle cell disease always causes anemia, but it causes much more than anemia. That's why we call it sickle cell disease now. Helpful?
Okay, so I just need to understand anemia. What is anemia then?
Anemia means you have a low blood count. So people can be iron deficient and they'll become anemic. People can have primary issues in their bone marrow and they become anemic. There are a lot of reasons that you can be anemic. So you will trait and be iron deficient and you will be anemic because of the iron deficiency, not because of the sickle trait.
Okay. Okay.
Right.
Great. All right.
Okay.
Got it. Thank you.
Can I ask a question?
Of course.
From your professional experience, how important would you say food choice is and nutrition is in managing sickle cell? And on your Ghanaian roots, are there any particular foods that have been known traditionally to have an anti-sickling impact on the blood?
That's the next. I'll take the first part related to Ghana, and then I'd like Ted to shed some more light on it. So, growing up, I grew up in my grandmother's home. At some point, I had to go live with my grandparents, and it's a house full of kids. That's how Black folk do. That's how we just are. We take care of each other. And two of my cousins had sickle cell. One of them unfortunately died from it, but the one that survived, when she would have pain crises, we had no clue, what was going on. We were kids, we thought, they were possessed by some, who knows what, right? That's our understanding. But one thing that was sure for us to know that she knew her triggers. She knew when she was going to have crises, the body temperature, where she is, traveling, stress, all kinds of stuff, right? So I, indirectly, now that I know a lot, yes, there's certainly some natural fruits that actually contain compounds like a compound called 5-HMF that acts very similar to actually the drug that we designed in voxelotor and oxybryta. It increases oxygen affinity, and I was going to get to that eventually. But there are some natural fruits that contain this agent, for example, that when you eat can modify hemoglobin in such a way that it controls how much oxygenated hemoglobin you have in each red blood cell. That prevents colonization from happening. But those natural molecules don't live long enough. It's important to be bound to hemoglobin, stay on hemoglobin for the duration of the cycling of that red blood cell as it leaves the lung, goes to the tissues, back to the lung, and it does that over and over and over again. So if you eat fruit that contains this agent 5-HMF that modifies hemoglobin, you're getting first very little of it. You're modifying very little of your hemoglobin, right? So while some cells may be protected for a short little time because you have 5-HMF in your red blood cells, it's not an ideal drug, if you will, because you can't control it. You don't know how much you're taking, and it doesn't live long enough to protect the hemoglobin from the process, the detrimental process. But yeah, certainly, in Africa, for example, because there less access to drugs that can address some of the pathophysiology of sickle cell disease, people do all kinds of wellness stuff to keep their vitality, right? They also prevent things are triggering for them in terms of vaso-occlusive crisis, for example, right? And I'll leave it there. I wonder if Ted, you have anything to add?
Yeah, I'll just add that yes, food, good nutrition, good exercise habits help everything, but not nearly as dramatically as getting rationally designed power therapy to treat the underlying problem. And the analogy I would give you would be, let's say that two people develop lung cancer. very fatal disease. One person is homeless, getting no nutrition, no support. I think that person is likely to die with the exact same disorder more quickly than the patient who's got a family, eating 3 square meals a day. But what's really going to change the outcome for them is to get surgery to cut the cancer out if it's operable, or to get powerful medicine. Same would be true with HIV, right? If you get on the right therapy, we could completely contain your HIV. But if the individual with HIV on the street and the individual in a nice home, neither one are taking therapy, they both are going to die pretty quickly. What's going to make the big difference is getting appropriate treatment. So I think, we always encourage people with any disease to live a healthy life and to eat good food and do the right things. But powerful interventions, really like Kobe's describing today, are generally the result of really high quality science attacking the fundamental basis of the disease, which food typically can't do.
Quick question, following up with what Kristen had mentioned. Calvin had asked a question, and I'm not totally sure if this was already answered, but which fruits contain combination proteins that help hemoglobin? That's her question, if that can be answered.
So I'd have to go back and check, but BioHMF, it's just one example, and I need to go back and look at the literature too.
It's generally sweet stuff.
Yeah, sweet stuff.
It's generally sweet stuff, which may have some problem eating too much molasses. But you could never
more comment before we move forward.
Just one other thing, but you could never eat enough fruit to modify enough of your hemoglobin to do what Kobe's going to describe. Yeah. You would probably burst your stomach open trying to eat enough fruit to even get close to the kind of, because they're doing the same thing as he's pointing out. But you could never eat enough fruit to get close to the things that Kobe's going to describe for you.
Okay. We had saw a presentation by Dr. Fatima Jackson. She's a doctor out of Howard, and she was discussing her PhD work that she did in the Gambia, around cassava. And she said in the northern region, she found that there was a high frequency of sickle cell, but it wasn't into the unmanageable state because cassava was eaten as a staple food, which means every day it was put on the plate. And in the southern regions where cassava wasn't grown abundantly, there was a higher expression of the phenotype, the genetic expression, and the disease because the foods were not grown at the same frequency. So that's why I asked that question, because there were other alternative approaches to understanding how food could serve as a managing agent in still having the genotype, but necessarily that phenotype.
Yeah, I'll just emphasize that any physician that's well trained, hopefully like me, will always encourage you to do healthy living. But you're not going to stop HIV with a diet. You're not going to stop sickle cell with a diet. You might be able to augment it, because there's no doubt that being better hydrated is really good in sickle cell disease. And that's simple water, right? Definitely managing certain things around altitude, being at high altitude exacerbates sickle cell disease. So there are a lot of things that can have some augmenting effect, but if you're trying to really shut a disease down, like we can shut cystic fibrosis down, that's a genetic disease that primarily occurs in white people. These little these filaments in their lungs don't work, and so they can't move the mucus out of their lungs, and so they end up dying because they have all this mucus in the lungs. Well, Vertex has these therapies to make those cilia move normally again, and that has had a much bigger impact than any kind of healthy diet. In fact, most of those patients now are looking at a normal life expectancy, whereas when I started training, those patients were typically dying in their late teens and early 20s. So again, always want to encourage people good diet, but we've made CF basically a non-fatal disease now by designing very rational therapies to correct the fundamental problem, which is in this case, the cilia doesn't work, and sickle cell disease, as Kobe's described, your hemoglobin is sticking together in this inappropriate way. And we think you can stop that with a simple molecule that binds to the hemoglobin.
Thank you.
Got it.
Most welcome. All right, so I'll try to move forward, and let's see, and then we'll have an opportunity. Okay, so sorry, I've been over all this already. Okay, so the idea, after talking about the cascade, the idea is, could we regulate this process? Could we block this process with a small molecule in a red blood cell so that it doesn't have the opportunity to sickle and then have all of the downstream sequelae, right? So the idea is, if you block polymerization upstream, then your cells, you won't get polymerization and your cells won't sickle, they won't lyse, they won't also block blood flow, and you won't have all of the downstream sequelae. And we know that putting oxygen back in the system does that. The question is, could we use a small molecule to control that process? So just a quick summary, because we've had discussions already. I've talked about sickle cell disease. I've talked about some basic biology. I've talked about where it is predominantly. I've talked to you about clinical symptoms. We've talked about the roles of red blood cells and hemoglobin, how there's an amplifying effect to be able to carry oxygen in the body. We've talked about sickle hemoglobin sticking together in a process we fancily call polymerization as the root cause of the disease. And I've talked to you about what happens and how polymerization cascades into all of the downstream sequelae, including anemia, pain, organ damage, and ultimately death. I know we've had a lot of questions, but I want to provide another opportunity if there are more questions at this stage. If not, I'm happy to move forward. And are there any more questions? Or
We are
Yeah,
my apologies. We are, Kristen, just before you, we are currently about 5 minutes before our intermission. And just for people that have questions in regards to treatment situations, that will be talked about in the secondary portion of the presentation, just so that you guys are. Go ahead, Kristen.
prior to you developing this particular treatment, what was it about Western medicine's approach? You know, I'm only assuming that you got your PhD in the States, right? So
Yeah.
what was it about the medical process here in the Western world that you saw personally? Because I know there's a lot of people, like you said, maybe in Africa, who don't have access to the particular technologies that are available here in the States. But what was it about the treatment plan that you were exposed to that made you say developing this alternative is a necessity?
yeah, and that's a great question for the second half, because that's what I'm going to focus on. But just to give you a little flavor into it, because my understanding is we'll go to break at noon. You know, we took cues from how nature itself has modified this disease. Now, the opportunity to work on it here in the US, the only difference between that and Africa, for example, is that here you can bring scientists together, raise money, have them focused on a disease that, quite frankly, had been ignored for a very long time, right? So that's exactly what we've done. And you know, I'm so fortunate to have had Ted be, you know, the leader to be able to raise money and you know, build a group that is focused on designing a drug that specifically addresses the malign cause of the disease. Now, if you don't mind, perhaps when we come back, you know, from break, I can go into it, or should I, Antoine, should I go into it now, or?
And, you know, Kobe, I'm going to suggest, since we're so close to the break, maybe you just start your second half after the break.
Okay.
But maybe to answer this question a little bit, I'm 64 years old. When I was a kid, people in general with sickle cell disease were dying before their 20th birthday. Even when I went to medical school, it was pretty common for sickle cell patients to die in their 20s. What Kobe kind of has described as how the organs are being killed by sickle cell disease. One of the first organs to be killed by sickle cell disease is our spleen. And what your spleen does significantly is protect you from infections. So what we realize is that most of those individuals dying of sickle cell disease when they were 15, 16, 17, they were dying of infections, gram-positive infections specifically. So what we did in Western medicine that made a big difference to stop that was we started giving all of those children prophylactic penicillin to protect them from gram-positive infections. And we also gave them all vaccinations. And those interventions basically covered up for the fact that they had no good spleen activity anymore. So they stopped dying of these infections because you had kind of covered up for the spleen problem. So that was an example of treating a downstream consequence of the disease and extending the survival of patients without treating the fundamental problem. You didn't stop polymerization, you didn't stop the sickling, you didn't stop the anemia, but you did step in and provide some protection from this loss of splenic activity, which leads to higher rates of infection and death from infections. And we were doing that in the US, and we continue to do that well in the US, which is why dying of infections has become really a non-issue in the US. But it's still a very big issue in many parts of the world, in Africa, and that's why the majority of kids with sickle cell die before they're even 5 years old. Did that answer your question? I wanted to make sure, because I think you were asking about the US and our differences and why our outcomes are different potentially.
Well, I think you gave some insight into, your history of being exposed to the disease and what made you want to put another layer of what's going to be expected by the community in advancing our genetic, position.
Yeah.
I was thinking more like, what was your moment that you experienced that said, this is not working here and we have to develop something else to do it. I do appreciate, because you gave more of like a historical lens. And I think that was good. But I'm thinking more like on a personal, like what for you was that transformative moment that said it's necessary for us to do something else, because everything that is being brought here, it doesn't seem to be meeting the root of this issue.
Yeah. So I'll give you a good example.
My apologies, Ted, really quickly. After you answer this, we're going to go to break.
Okay. All
right.
So I'll give you a really good example. When I was a medical student at Yale, we started having these patients come in with infections that we had never seen before. It turned out to be the beginning of the AIDS crisis. These patients were coming in with what we now have AIDS. And they were primarily back then dying of an infection they get because of the AIDS killing their immune system. They were dying of pneumocystis carinii. So we had a drug called pentamidine that would treat cystis carinii. So we were able to help people live longer with HIV. And then we even started to give them prophylactic, just routine, even when they weren't infected, exposure to pentamidine. And we showed that we could extend survival, but we could never make things normal until we killed the actual virus that was causing HIV. And that's what changed it. So by analogy in sickle cell disease, we've been treating the downstream things like the pneumocystis carinii. And what my view was that we needed to treat the virus, in this case, the polymerization, because the polymerization is driving the disease. So that was the aha moment, and that was the reason that I joined Kobe to try to turn this idea into an actual therapy that we could make available for patients around the world.
And if I may add quickly, for me personally, it was really watching my cousin, because I said, like I said, and as Ted mentioned, infections are a big deal in patients who have sickle cell. I lost my cousin, Oli, very young boy at 5 years old, because he had an infection and he couldn't tolerate. My cousin, who is now a teacher, is the one that I was most close to, and I had the most experience with sickle cell disease, pain crises, just watching her go through it. And I'll never forget, after I immigrated here to the US and had the opportunity to train as a scientist, right, and actually had this opportunity to work with Ted to address this disease, directly, that, while she was suffering and going through, pain crises and was anemic and all of these other things, she really didn't have any choices. There was nothing on the market she could take to actually, deal or lessen the effects of the disease, right? And as Ted put to it, there were a few things on the market that address the downstream effects of the disease, but no one really was looking at the fundamental issue causing the disease, which by measure for a lot of other diseases, such as cystic fibrosis, as Ted mentioned, is the way that typically scientists and doctors will approach drug treatment. So we had the opportunity to do that, and it made a lot of sense. The other thing that really impacted me, my cousin waited and waited and waited and waited until she was able to find someone who had sickle SC, just because she wanted to not her kids to have sickle cell disease. So the impact of having the disease is profound, as you can imagine. I'm sure you know people who have it, right? And so for me, those were the factors that came together and really promoted me to come and join Ted's team in GBT to address this issue head on. And I'll be glad to walk you through. I won't bore you with a lot of the science behind it, but I'll talk about it. And I'll talk about where we took cues for. I learned very early on that, for a lot of issues in life, because life has had time to evolve over time, that in fact, there are answers. If you know where to look, there are answers everywhere. The question is, can you copy and have a more defined focused therapy to treat sickle cell? So with that, I'll leave that. When we come back, I'll talk about, how we approached it.
Incredible. Incredible. Thank you so much for that synopsis. That is awesome. All right. We are back to our schedule. Please, if you guys filled it out, remember, just shoot a message to the text. Nadina and I are co-moderating this presentation, so we'll be able to get your messages from there. But thank you so much. We are going to hand the mic back over to Kobe and Ted. Presentation is yours, gentlemen.
Thank you so much. You can still hear me, right?
Yes, sir.
Okay.
Loud and clear.
All right. So the next phase was, how do we prevent hemoglobin sticking together, or hemoglobin explosion, with a pill? And as I mentioned previously, we took heed from clues from nature. I learned very early on in life that, like I said, most of the issues that we deal with, if you know where to look, you'll find clues in nature already that actually address these issues. So unlike sickle hemoglobin, which is called hemoglobin S, which I talked about, there are two other types of hemoglobin. Hemoglobin F is what we call fetal hemoglobin, and that's typically hemoglobin that is present in a child while it's in its mother's womb, right? When it's a fetus. And the reason for having a different type of hemoglobin than what we call adult hemoglobin, which is hemoglobin A, is that, as you can imagine, oxygen is so important for development. And while a mom is carrying a fetus, the fetus is not exposed to the outside. So the fetus has to find a way to get some of that oxygen from mom. How does it do that? By having hemoglobin F as opposed to having adult hemoglobin A. Hemoglobin F has a stronger pull for oxygen than hemoglobin A does. And therefore, when mom breathes in across the placenta, because the fetus's blood, or the baby in the mom's womb's blood, has hemoglobin F that has a stronger pull, what does baby do while it's in the womb? It draws some of that oxygen, so that it now can have oxygen, to be able to develop while it's in its mom's womb. Now, after birth, the hemoglobin F expression is supposed to go away, And then the baby, after about 6 months, starts making adult hemoglobin, right? Because now the baby can breathe, it's outside of its mom's womb, it can breathe in air and act and behave normally as adults adults behave by breathing in oxygen directly. Now it turns out that unlike sickle hemoglobin, both hemoglobin F and hemoglobin A, whether oxygen is bound to it or not, does not have multiple sticky ends, so they do not polymerize. It also turns out that in nature, sometimes, remember what I talked about, so, after the baby is born, hemoglobin F levels have to go down significantly and are replaced by normal hemoglobin A levels. But sometimes the switch doesn't occur very, proficiently. What happens is that a child is born and they continue to express some level of fetal globin, which really doesn't affect the child. It's not detrimental to the child. And as you can see, in fact, in some cases like sickle cell, it's very protective. So it turns out that if a child is born that has sickle cell disease, but continues to express, in addition to sickle hemoglobin, express hemoglobin F at ratios greater than 20 to 30%, actually more like 30% in every single red blood cell, that hemoglobin F, because it's present in the cell together with sickle hemoglobin, it gets in the way of sickle hemoglobin sticking together to form polymers, to form those long rods that I showed you. And therefore that inhibits polymerization effectively. In fact, in patients, yes.
I'm sorry, can I stop you for 1 second? There was a question further up in the chat, and I'm not certain if it was answered. It was, can Oxbryta help people with the trait?
That's a great question. So for the most part, sickle cell trait is considered benign, but actually we've learned that at a much, with age, they can have a lot of kidney complications. There's a reason for that, actually. So the kidney is one of the most hypoxic, a fancy word of saying, the kidney is a region that has very low oxygen levels. Now, it turns out that even when you have sickle cell trait where you have 50 to 60% normal hemoglobin and only 40 to 50% of sickle hemoglobin per red blood cell, even though you can inhibit polymerization by having hemoglobin A at really high ratios, when you get to the kidneys where the oxygen tension, meaning that there's really no oxygen at all, a lot more oxygen comes off, and you can actually have sickle hemoglobin stick together. So you'll see that those who have sickle cell trait over time will have some issues related to kidney function because it's a very sensitive organ in terms of oxygen levels, right? And from that respect, I actually have a paper that showed that you can take trait red blood cells, add Oxbryta to it, the voxelotor to it, and then take those cells. Remember, I took red blood cells and I put it in a condition where there was no oxygen and it's sickled. But you can actually show that you don't get a lot of sickling because now you have compound. So not only do you have hemoglobin A, which doesn't polymerize, but Oxbryta modifies sickle hemoglobin.
Oh man.
Exactly. So that such that a part of it, whatever sickle hemoglobin is bound to Oxbryta, cannot also polymerize. And that's what I'm about to talk about, right? And therefore, yes, we haven't done the studies, but I envision from a mechanistic perspective that yes, taking Oxbryta may be useful in those scenarios as well, right?
Okay. All right.
With a caveat that we haven't done any work on it yet.
Okay, I have one more. I'm not certain if you answered it. The question is, now that we have a good number of persons who are taking new treatments like yours, do we have plans to track and report effects experienced and share outcomes experienced?
Yeah.
Can this change prescribing practices of HCP and availability to people desiring these drugs?
I'll answer part of it. I'd like Ted to shed more light on it. Absolutely. We never stop tracking. It's called phase 4 studies, right? Every patient that's on Oxbryta and any other drug for that matter, if they have any issues, any adverse effects, things that are unexpected that are not part of a label claim, the label really describes what is expected you're expected to treat, right? And so any outcomes that are outside of that realm has to be reported, right? So yes, those are reported and we capture that. And actually that forms a part of the impetus for us to design even better drugs in the future, which I will talk about. Ted, do you have anything else to add?
Yeah, I'll just add, Nadine, it's a great question. And I'll just tell you, this is almost always the way it works in therapy development. that we initially look at something that we think is really going to change outcomes, but it takes a longer time to measure the outcomes. And as you guys know, I'm a cardiologist, and one of the first big experiences that's relevant for me is lowering your cholesterol with good cholesterol lowering drugs. Back in the early days when we had these drugs like Lipitor, Mevacor, we knew we could lower your cholesterol, and we actually even saw that it could reduce the blockages in your coronary arteries. And we thought it would change your risk of stroke, your risk of heart attack, your risk of death. But it took a long time to show those studies. However, when those studies came out, which is probably 5-7 years after those drugs came out, the effects were huge. 30% reduction in death, 30% reduction in stroke, 30% reduction in amputation of limbs. Because when you treat the underlying problem, it's kind of logical that those things would follow. The same in HIV. Initially, all we were showing is we were killing the virus. But when the studies read out, we completely were stopping death due to HIV. But it took longer to show that. So those longer term studies are really important, and they will be done, and that data will be fully shared.
Thank you.
Okay, so to proceed, and I'll be brief with this description, we have an idea that if you can block polymerization and you have enough of an anti-polymerization potential or stickiness, you can control that process with either hemoglobin F or hemoglobin A. Or if you remember, if you can control the process even with sickle cell, with sickle hemoglobin, keep most of those molecules, greater than 30% of those molecules, and with oxygen bound. If you recall what I showed you back here, if I may revisit that, just so that you know there is. So basically, if we can control this process with a small molecule, then we have fewer molecules that have multiple sticky ends, and therefore fewer molecules can stick together and form long extended polymers. So that's really what we were trying to do, and exactly what we did. So let me quickly go back to where I was. My apologies. Yeah, so I've talked about HB and HBF as examples, and we took heed from how much protein sickle hemoglobin we would have to modify for it to block the process of sticking together completely, so that the cells don't sickle and cause all of the downstream sequelae that I've described time and time again. So our idea was design a small molecule that regulates this process, right? That keeps most of greater than 30% of the hemoglobin molecules in the red blood. So remember I said we have 250 million per red blood cell. Our goal was to modify 30% of that. By modifying 30% of that based on the examples that we've seen from nature, we knew that that was enough to protect that red blood cell from polymerization and sickling, and therefore all the downstream sequelae. So one of the biggest, I'm not going to bore you with how we did that because it's a bit more technical, but one of the biggest challenges, and the reason why you can't, as Ted mentioned, you can't eat enough fruit to actually fix sickle cell disease, is what I've talked about already. You have millions of red blood cells, okay, and each red blood cell contains greater than 250 million hemoglobin molecules. If you're trying to modify 30%, goodness, you're going to have to take a lot of compound to be able to modify each one of those. Now, it's also a drug. It's important that you design it to specifically go in the body to bind to your target, which in this case is sickle hemoglobin and nothing else, because you don't want to be having, your compound all over your body doing God knows, what, right? So those are some of the challenges. It was also important that we demonstrate that the drug is safe in clinical studies, typically in preclinical studies as well as clinical studies. So this is why you can't eat enough fruit, and you actually will have to take a drug that has the propensity to bind to hemoglobin, stay on hemoglobin, so that you can continue to take more that adds on until you get above that 30% modification, which was the threshold that we needed to be able to ask whether we have benefit, similar to trait, as well as what I mentioned, the HbF angle called HbFH. Okay, so when we did just that, like I said, I'm not going to go through the iterations of what we did. It's very complex. You take, hemoglobin structure. You do. This is what we're trained for, right? So this is what we did, and we were able to be successful with voxelotor, which is now called Oxbryta. So one of the earliest tests that we did to demonstrate that this will work, we did a very simple experiment. We'll take red blood cells from sickle cell patients. We will expose the cells, as I've showed you in the videos, in environments where there are no oxygen, and then reintroduce them to environments with the oxygen. And they have the cyclical nature of when you put them under conditions where there's no oxygen, you get the sickling, as you can see here. When you bring them back to conditions where there's oxygen, they go right back to their shape. So we do this over and over and over again to recapitulate what happens in the body as a red blood cell travels from the lung to your body or your tissues and comes back to the lung. And what happens is that with every round, as you can see, if in the graph, this graph, if you don't have any drug or voxelotor on board, you see the number of sickle cells increases dramatically. Whereas when you have about 30% of that, of each of the hemoglobin in each red blood cell modified with voxelotor, you don't have more sickling over time. I hope that's clear. This was very exciting. I remember the day I personally did the first sickling experiment with sickle cell blood. I could not believe it when I titrated compound into it and I exposed it to low oxygen tensions and realized that the cells stayed the same. They didn't sickle. It was, again, one of the other moments, if I haven't described already, I couldn't believe it. I went home with a big smile on my face because I knew right away that, we had something. But it's easier said than done when you take cells from the body and you add compound to it. Remember, the way we introduce drugs in our body, sometimes we take it orally, sometimes it's by injection, and the body is more complex. It's not only hemoglobin or a red blood cell. There are eye cells, liver cells, all kinds of stuff. So you have to design a drug that's very specific. That when you take a pill, it goes straight into the red blood cell. It binds to hemoglobin. It stays on hemoglobin for as long as it can and protects that hemoglobin so that you don't have the polymerization event. And the way we do this is by carefully initially doing animal experiments, in models where we, I don't want to go into it. We've created scenarios that the animals have sickle cell. We test the efficacy, but eventually you have to do the experiment in people, and we're very careful about how we do that. We very slowly give patients, or first healthy volunteers, very little amounts to make sure that it's safe. Sorry, someone can mute there.
My bad. I'm sorry about that, guys.
No, it's okay. So before we go into sickle cell patients, and then continue to give multiple doses while we evaluate safety and efficacy. Okay, so
I got to stop you.
Yeah.
Okay, this is a question.
Yep.
I think it's kind of twofold. I'm not certain, Mr. Brown. How can we effectively address the historical impact of colonialism on the widespread prevalence of sickle cell disease while simultaneously promoting accountability among the dominant class? Now, that's the first part. Then he goes into, moreover. So I don't know if you want me to read it all. Do you want to answer that one first? Or you want?
It's a big question. I'd like Ted to opine on it as well, but it's a social question, and a part of what we're doing now is key, is central to it. Education, right? Teaching people about sickle cell, its origin. Mutations happen all the time. They happen all the time in population. Sometimes they actually confer positive outcomes in people and their exposure to diseases. Other times they cause disease, right? So, and understand the history of sickle cell, how it came about, who it affects, our history, why we haven't received treatment consistently, why we've been marginalized. All those are conversations that I think must be had so that we can all come to the table and understand when a patient goes to the hospital, they're suffering from pain and they ask for a narcotic to modulate their pain, that they're not seeking drugs to get high, but they are in pain and they need to, so education and is central to this, which is why it's a part of why we're doing this. I don't know if Ted wants to add more.
Well, I think you're right. I mean, what I would just emphasize, which you already made the point of, is we many times need to be the own provider of our solutions rather than expecting somebody else to come in and solve our problems. And in fact, that was a big part of why we created GBT. We felt like it could be a company created by people of color, run by people of color, who would really focus on doing the right thing for people of color. GBT actually became the largest investor in the world, including the US government. We were investing more money in trying to solve sickle cell than any other entity in the world. So one solution to the colonial disregard, our historical disregard, is fix it ourselves. And that's what we tried to do at GBT. That doesn't mean that you don't try to deal with the social issues, but we really felt like this is an opportunity to empower ourselves through education, through building a company, through coming up with a solution, and not trying to convince other people to put down their racism, put down their discrimination, and solve the problem. We decided we'd try to solve it ourselves.
Okay, so let me just finish up. Moreover, how can we navigate collaborations with these dominant class entities, particularly in the context of selling solutions for sickle cell disease while still ensuring that affected communities maintain a significant level of control over the initiatives and solutions developed?
Maybe what I would suggest is, Kobe and I are physician scientists. We're not really ethicists or anything like that. You're probably getting kind of beyond our skis. There are social issues. We don't want to deny that.
Okay.
But honestly, we're physician scientists trying to find a medical solution, not really primarily focused on the social issues, which are very important, but that's probably a different session than what Kobe's trying to educate on today.
Not a problem. How can we design effective policies that cater to the dietary requirements of the sickle cell community within grocery stores? This all sounds social once again, I believe. Community within grocery stores, taking into account the detrimental effects of the standard American diet's chronic inflammation. Further,
I think this is an issue of their food deserts in the U.S., but that has nothing to do with sickle cell.
Sure.
It disproportionately affects our community, which disproportionately affects sickle cell. But I think we need a more fundamental solution to that. I don't think we're going to be able to engineer a solution at GBT or, in a company to come up with a molecule to solve that. We need to have a more, extensive social policy about who we elect, vote. We don't want to get into that, but I think those
absolutely.
are the solutions.
These are just questions. I'm just putting them out there so that everybody knows that we didn't overlook them. Now, how is Oxbryta?
No, I get you.
How is Oxbryta? Okay. Oxbryta different from hydroxyurea?
Completely different. Hydroxyurea is a chemotherapeutic. It's a cancer drug, and it suppresses the bone marrow. And by suppressing the bone marrow, you're able to generate what we call a stress response. And literally genes in the body that relate to fetal stress turn on. And one of those genes is fetal hemoglobin. So you can generate a little bit more fetal hemoglobin, which does not polymerize. So it's really kind of trying to do the same thing, but it's kind of doing it by suppressing the bone marrow. It's not really a direct solution. And obviously it's a cancer drug, so it wasn't really designed to treat sickle cell disease the way Oxbryta is.
Okay, this last one here, in the earlier slide about the in vitro experiments, what do you mean by cycles? In the earlier slide about the in vitro experiment, what do you mean by cycles?
Right. So we take a red blood cell and we expose that red blood cell we put it in a chamber where there's much less oxygen than you would find in the normal surrounding, right? So it's called a hypoxic state. We take a lot of oxygen out of that chamber. And so that red blood cell is now sitting in a situation, and the only thing that can happen with the oxygen that's bound to the hemoglobin is that it comes off. That's by design. That's how hemoglobin works. That's actually how it's able to pick up oxygen in the lungs and deliver in a tissue. In your environment in the lungs, there's a lot of oxygen. So hemoglobin would bind to the oxygen. When it gets into, for example, your liver, where there isn't a lot of oxygen, hemoglobin will release that oxygen, right? So what we're trying to simulate what happens when hemoglobin transport oxygen from the lung to the tissues. So what we do is we take red blood cells from a patient's blood, we modify it with compound, or as a control, we don't add any compound to it. And those red blood cells are put in the chamber where initially there's no oxygen. We also have a way of reintroducing oxygen. We take oxygen away again and reintroduce oxygen. So we have multiple cycles of oxygen present, oxygen not present, oxygen put back into it. And as you can see, the cell is round initially because there's no polymers. As you continue to take oxygen out of that chamber, it sickles, right? Because you form polymers within that cell, right? You have the stickiness that I've described. Now, when you put oxygen back in the system, remember, now oxygen binds and it goes from its non-sticky self to the, it goes from the sticky self to the non-sticky self. So the polymers break apart, right? And the cell goes back to its normal shape. Now, with every round, you don't get complete melting of the polymer. So when you go to the next round, it's easier to actually form long rods because you already have rods in that cell, which is why with multiple rounds of oxy-deoxy, you see that the number of sickling cells or sickled cells goes up, right? And actually that this is typically what happens in a patient, right? Red blood cell that's fine initially picks up, oxygen in the lungs. As it travels to the kidney or the liver, it dumps the oxygen. What happens is that there's a polymerization event, sickling event, and sometimes some of those cells can return back to the lung. Now, as they go back to the lung, it's an oxygen-rich environment, so the polymers melt, right? The stickiness falls apart. Sometimes it's not complete. There's some residual polymers that are formed still in that cell, even though that cell is round. So the next round of going into a hypoxic circulation, the tissues, is even worse because now they can stick together even quicker because you already have some seeds that are present within that cell. So with every round of that life cycle of that red blood cell picking up oxygen and offloading, you can get more sickling events. It gets worse and worse and worse. And what we're showing here is that you can see the number of sickled cells in circulation, in the experiment goes up with multiple rounds of deoxy-oxy, whereas when you treat with Oxbryta, you see that it's flat. And that's an important measure. To me, this is a very profound experiment that demonstrated that if we can achieve that 30% modification of the total hemoglobin in circulation within the body, that we can block polymerization or the stickiness of hemoglobin so that they don't have a sickling event and then all of the downstream sequelae. I hope that answered the question. Should I move on? Or?
Okay, yeah, go for it. I don't have any more. So yeah, he said, yes, it does.
Okay, excellent. All right. So the question is that, as I said, we have to, just because the drug works outside of the body doesn't mean it's going to work in people. So we have to do studies in people. Like I said, we're very careful about how we do these studies. We take our time. We initially introduce very little doses of drug in healthy people. Then we go to the highest dose that we can before we start studies in sickle cell patients. So we ultimately did studies with Oxbryta or voxelotor in sickle cell patients, and our target was to get to greater than 30% in every single red blood cell in circulation. Right now, how do we know that usually the drugs of design work? We have to go back to the pathology or the pathophysiology of the disease, and I think I've talked extensively about it. Sickle cell patients are anemic because their red blood cells explode and release all of the hemoglobin. Their red blood cells are destroyed in circulation, right? So they have less hemoglobin. So when you give a drug that fixes this issue of polymerization and blocks sickling in the downstream sequelae, you expect hemoglobin levels to rise back up because the cells survive longer in circulation. So that's one indication. We also expect that we don't see sickled cells. As I've showed you in my first slide, you see the sickle cell shape in the smear of the blood, right? We also expect the patients not to have some of the downstream sequelae, including pain crises, VOC. We also expect the patients, because they have more hemoglobin, to feel better, to be more energetic, right? And clearly, having some of the acute and chronic manifestations that I talked about, then they would have no reason to visit the hospital frequently. So that's how we know that the compound or the drug is working when a patient takes it. So with that, I'll briefly describe some of the experiments that we've done. So typically when you do these clinical studies, there is a cohort that receives a pill, but that pill doesn't contain active drug. It's placebo. Now, most of the patients in this study were already on hydroxyurea, so they have some underlying protection already with the regimen for treatment of sickle cell disease. So you have what's called a placebo group. They're given a pill, but it doesn't contain active compound. Basically, there's no voxelotor in there. And then we also evaluated 2 doses of voxelotor or Oxbryta, 900 milligrams and 1500 milligrams. Now remember, when a person takes a pill with an active drug, a certain amount of it is absorbed into the bloodstream, which then distributes into the tissues like red blood cells and binds to hemoglobin. Right? It's called the pharmacokinetics. It's a big word, but all it means is when you take a drug, how much of it can go into your target, which in this case is hemoglobin, modify it, and then give you the benefit of why you designed the drug in the first place, right? So you have 3 classes, and what we're looking for, the easiest endpoint here to look for was a hemoglobin response. Can you increase hemoglobin? By increasing hemoglobin, you're already demonstrating that you're preventing polymerization, the hemolysis that comes, the explode, the cells lysing, right? You're protecting the cells from polymerization, so they live longer, and so hemoglobin levels go up. That's how we know it works. There are other things that we also looked at. When a red blood cell explodes, there are these proteins that are released into the bloodstream, and you can measure them, and that gives you an idea of how much hemolysis you have within the bloodstream. Also, because your bone marrow works twice as hard to make more red blood cells to compensate for all of the cells that you're losing, because you have these non-viable cells with rods in them that are exploding. Because your bone marrow can make more to replace those, you have these early young red blood cells called reticulocytes that are much concentration than they should be in a person without disease, right? So those are the indicators that we can follow to ascertain whether or not the drug that the patient has taken, if it's an active drug and not the placebo, which doesn't contain active drug, that there is efficacy, that there is a change in the pathology of that person, right? That person is benefiting from taking that drug. I hope that makes sense. So that's exactly what we did. We did a study. This is one example of the study where over the course of time, patients that received placebo, as you can see, had no change in their hemoglobin throughout the duration of the treatment. Whereas the 2 doses of containing active drug of 900 milligrams and 1500 milligrams, you can see there was a dose-dependent response in how much hemoglobin that they received. And what that means is that we were able to voxelotor block polymerization in a dose-dependent, which makes sense because the more hemoglobin molecules you can modify, the less they can go into a polymer, right? If you remember. And therefore, we saw a different effect. One of the things that I love the most is at some point when the study ends, it's important to consider those who are on placebo because it's unethical that they're on placebo. And I remember most of those patients are on HU, so they have some level of protection. And the efficacy that we're measuring here is on top of HU. But what we do, which I think is very important, is those that are on placebo, once the study is over, we then give them drug so that they can also benefit from it. And you can see at this point, when those patients are given drug, they have a strong hemoglobin response as well, right? Which demonstrates that the drug is doing exactly what it's designed to do. Additionally, as I mentioned, if the drug is working, then look at the blood smear. You take blood, you put it on a glass slide, a nerdy guy like me goes into the lab, looks in the microscopes and looks at, how many sickle cells are on that. It's obvious. You can see how many sickle cells are in, for example, this blood slide. It's very clear. But when you treat with voxelotor or Oxbryta, you can see 2 things. One, there are fewer cells. I think here I can only count 1 cell that's still remaining, right? But most of the cells have the normal shape as you anticipate. And not just that, as you can see, there are more cells, right? Because you're stopping the cells from bursting, right? From being destroyed in circulation. I hope that also made sense, but I'll ask the questions. I'll give the opportunity for questions later. We also realized that there was a correlation between how much hemoglobin, how much benefit that patients were observing and their propensity to have vaso-occlusive crises. These data demonstrate and indicate that a drug that is even more potent than Oxbryta and puts most of the patients within the normal range of hemoglobin, what the normal range of hemoglobin is for a person, which is greater than 12, will benefit the most from prevention of VOC. That means that they have more quality cells in circulation, right? And therefore they get more benefit in terms of blocking all of the downstream effects that comes with targeting the underlying cause of sickle cell disease, which is hemoglobin S formation. In addition, in larger studies and in a combined observation report from patients who are taking Oxbryta in the real world, we've demonstrated that we've impacted the reductions in transfusion, which makes sense. If you're increasing, you're getting more hemoglobin and you're less anemic, you no longer have requirements for transfusion. But notice the numbers, they are not 100%, right? Even though we're measuring differences and changes. So for example, reduction in number of VOCs, 23%, reduction in VOC-related hospitals, 34%, all-cause hospitalizations, 37%, so on and so forth. So while there's efficacy, it was very clear to us that we could probably do better, right? We can modify more hemoglobin S, and if we can achieve that and achieve it in a manner in which we learn from nature, right, which is sickle cell trait, as well as what we call HPFH, which I went into briefly, and we can achieve it at a 30% modification, then we expected actually, to get better efficacy. Now, from this, voxelotor is doing great because it's changing, it's improving anemia and actually reducing some of the other clinical phenotypes, including VOC-related pain, transfusions, et cetera, that I talked about.
I got a
Right,
question.
so, yes, please.
Can Oxbryta be used in combination with, and I don't know if I can pronounce this, thiocyanate to prevent sickle cell disease? Did I say that right?
Yeah, that's a very interesting. So thiocyanates actually they act very similarly, but it's not a safe approach to modify hemoglobin to prevent it from polymerization. It has been used and demonstrated that you can use that agent to do something very similar, right? Doing this example, we're intently designing a safe drug. It's because we're targeting an underlying cause of the disease. We do very careful studies that they're safe before patients starts taking them. It's the same reason why you can't eat enough fruit to fix your sickle cell disease. Thiocyanate has been regulated very well. In fact, the only experiment that I know that has been done, they took red blood cells and modified it outside of the body because thiocyanate is very reactive. If you took it and put it in your body, you probably will modify so many more things than hemoglobin itself, right? But if you took red blood cells from a patient, you modified it and you put it back in, and it blocked polymerization, yes, also shows that you can actually inhibit polymerization effectively and inhibit some of the downstream sequelae, right? So my proposal, I don't want to medical treatment and stuff, but thiocyanate is not necessarily in a form that's useful as a drug. That's my point. And Oxbryta, the only limitation with Oxbryta currently is the fact that we can give you more, which is why we have a follow-on compound called GBT601, which we're rapidly developing, and I'll share some of that data on that so you can see. I hope that answered your question. So just to quickly summarize, I've talked about some of voxelotor's clinical profile. We realized that it was.
I got a question, Kobe.
Yeah.
This, what are the side effects of Voxelotor?
I will leave Ted to speak to that.
It's been amazingly safe, which is why it got accelerated approval from the FDA. The most common side effects are kind of GI side effects, which tend to get better if you stay on the therapy over a matter of weeks. And that we think that's mostly driven by the amount of drug. It's 3 relatively large pills, which is exactly why Kobe continued to work in the labs to try to make a much more potent molecule that would be equally safe, but wouldn't be so much drug. So maybe it would clean up those GI side effects, but they are not serious side effects. It's not something like concern about causing cancer. It's not something like an irreversible effect on your body. It's mostly an issue of just some GI side effects that typically go away if people continue to take the therapy.
Okay, so you say these are 3 big pills that they have to take?
They're modest size. They're 500 milligram pills.
So do you intend to make those pills smaller or make them chewable or make them, easier to digest?
There is a pediatric formulation which is liquid, and adults could take that if they didn't want to take pills, and some adults do take it. The reason the pills are bigger is because of the amount of drug. As Kobe said, there is a ton of hemoglobin in our body, and that's one of the reasons that people felt this approach could never work, because you could never give enough drug to bind enough hemoglobin to do this. So voxelotor was a huge breakthrough, but as Kobe's going to describe in a few minutes, we thought we could do even better and come up with something that would bind even more hemoglobin than voxelotor and reduce the amount of drug and potentially reduce this nuisance side effect of GI tolerability. So want to make sure that Kobe gets to that. He's got about 12 minutes, so make sure he gets to that data for everyone.
Very quickly walk through that. So as Ted just said, voxelotor was efficacious, it's providing benefit, but the patient was able to achieve greater than 30% modification. And we knew right away that we could definitely, do better with a molecule. How were we going to do better? It's actually quite simple when you think about it. The reason why, the point was to design a drug that binds to hemoglobin and stays longer, so that when you bind to hemoglobin, whatever is modified is already modified. When they take another pill, it just adds on very quickly. And that's exactly what we've done. And that's why I've spent more time at the company continuing to develop an even better version of Oxbryta, which is currently in development. So yes, we can. I love that. Yes, we can. And I was taught, as a very young kid, always say, yes, you can do it. And if you couldn't, then, that's fine, but be positive. So yes, that's exactly what we did. So through several iterations of drug development that I've been that I won't bore you with, we designed a molecule called GBT601, which binds to hemoglobin and stays longer because of that. And because of its nature, how soluble it is, per dose. What's incredible is if you compare that to Oxbryta, voxelotor, per dose. So if you take 1,000, just as an example, 1,000 milligrams, you modify about 5% to 6% in a single dose with Oxbryta. Meanwhile, you're modifying about 20% of that already with the same dose. This translates to is a much smaller pill size, right? Mostly because what's called a fancy term, the pharmacokinetics of 601 is so much more improved over that of voxelotor, right? So remember, voxelotor is a very important drug because, like as Ted mentioned, groundbreaking. We demonstrate modify 30% of the hemoglobin in circulation for some patients, but not every single patient. And here we are we've done multiple studies, and consistently we can achieve greater than that 30%. So let me share some of that data with you. But first, let me talk about the design. So here's an example of the data that's already public that I can share with you. Because I can't talk about some of the other data that's not public. It's important that we have control of the information. So in this study, well, first thing we do after we've done a healthy volunteer study, which means we've been in small increments of the drug to healthy people, it's safe, nothing has happened, and we go into sickle cell patients. We want to see that when we give a single dose, when they take one pill, how much of that drug is in circulation, so that we know the baseline. Okay, this is where we're starting from. Now, when we continue to add more, how does it look like? So we give one pill, we let it wash out, right? At some point, there's no drug in the body. Then we give them a 50 milligram dose. We observe them for a while. They take that every single day for a certain duration. And then we increase the dose depending on where they are. So this is slowly trying to understand what dose will achieve greater than 30% hemoglobin occupancy, right? So that we can go into a subsequent study and give them, if, for example, that dose is 100 milligrams, just 100 milligrams over time, because we know that will push them above that 30% hemoglobin occupancy. Of note, same things we're looking at, same patient cohort, sickle cell patients. We're looking at primary efficacy of safety and tolerability. We want to make sure it's safe. It's really the primary thing we look at initially in every study. And then as a readout of efficacy, whether it's working, we look at hemoglobin and the effect on hemolysis and other markers, right? So I've conveniently put every time you see a graph with the red, I'm showing you where Oxbryta currently is in comparison to 601, okay, with a dotted line. So here, as I mentioned, most of the patients that took Oxbryta were lower than this, where this black curve, they were lower than 30%. You can see with just 100 milligram dose, remember Oxbryta is 1,500 milligrams. With just 100 milligram dose, we've already achieved greater than 30% hemoglobin occupancy, right? Meaning 30% of the hemoglobin per red blood cell is modified with 601. It's incredible stuff, really, right? Now, in addition to that, with Oxbryta, remember I told you most patients achieve greater than 1 gram per deciliter increase, right? There was a range of it, but the mean was 1 gram per deciliter. That's where the mean is with 1500 milligrams. With 100 milligrams, already you're getting an increase of 3.1 gram per deciliter. Now, if you are a person with sickle cell and you're anemic, but your hemoglobin is 9 or 10, plus 3 grams, you have normal, you no longer have anemia. You're basically in a situation where your red blood cells are not bursting, you're keeping all of your hemoglobin, you shouldn't experience the fatigue and all the things that comes with the deprivation of hemoglobin, because now you have normal hemoglobin levels. So you can already see from this chart the improvement from that perspective. Additionally, I think I mentioned to you the concept of what reticulocytes are. Now, because a sickle cell patient have their red blood cells being destroyed, the bones actually make your red blood cells. I didn't mention that, but your bones continue to pump out and make more red blood cells to compensate, right? To fix the fact that you're losing so many red blood cells. It can't quite catch up because the rate at which you're destroying cells having sickle cell disease is so much more faster than the rate at which your bone marrow is trying to make these cells. And what happens is that you have this accumulation that you store a lot many more of these very young red blood cells. They're called reticulocytes. They're very sticky. It takes time for these retics to mature, to become mature red blood cells, to function properly. And it's very stereotypical to have very high reticulocyte counts in sickle cell patients. Again, as an indicator of efficacy of the drug, you can see that to reduce reticulocyte counts by about 20%. With 1500 milligrams, with 601, at 100 milligrams, you're getting almost, greater than 50% reduction. Mind blowing. By the way, this is just 100 milligrams, by the way. You should know that we obviously are testing higher doses in current clinical studies that I can't talk about, but this is public, so I can share that with you. So again, relatively, you can see the improvement here. LDH is an enzyme, a protein, one of these machines I talked about that lives in the red blood cell. When the cell bursts or explodes, or whatever term you like, hemolyzes, that enzyme, again, it's another measure. That enzyme is not supposed to be in your plasma, right? So you can measure the concentration of it. That indicates the degree to which you have hemolysis or cells bursting. With Oxbryta, that's how much of a reduction we had, about 5%, 4.5% at 15 milligrams. With 601 at 100 milligrams, look at the degree of reduction of that. So 601, obviously, by design, and what we learned from Oxbryta's experience, that if we're able to modify greater than 30%, as I showed you here, that we more effectively inhibit normalization and all of its downstream sequelae, including reduction in hemolysis. Again, the cells, I always come back to the cells, because for me, it's self-evident. If you look in a patient's blood, a blood smear, you can see multiple cells, right? And this is a patient given 100 milligrams. I only see like one out of this millions. First, there are a lot more cells here in this field than there are. There's just only one cell here, the leftover with 100 milligrams. Mind-blowing stuff. I'm not here to promote 601. I'm just excited about these data because, as a scientist, that's just the way that I am personally. But it's very clear to me how efficacious the second generation drug in 601 is, and the potential it has. Of course, we'll continue to do very careful studies to make sure it's safe before it, like Oxbryta, it's rolled out, right? Those are the things that I can share with you. There's a lot more I can talk about, obviously, and I would just have to stop there because it's important that we don't promote our drugs before they're actually approved. That's important, right? So with that, I just want to summarize to say 601, Oxbryta is great. It is improving a lot of the pathology and the pathophysiology of many patients are benefiting from it, just from anecdotes that I've heard personally. In addition, but I want to say that even at 100 milligram dose, we know that 601 is more potent, and it has the potential, and Ted and I used to use this terminology all the time, to provide what we call a functional cure in a pill for a patient. Imagine take a pill, not because there are other ways to treat sickle cell. I'm sure you guys mentioned that you talked to another company that did it, which is great. But you have to go through a different process to achieve that kind of efficacy. There are lots of people in Africa who probably won't have access to those kinds of therapies. So if they can take a pill a day, and that can that can prevent most of the sequelae, and in fact prevent them from going to the hospital, that's great. And that includes my own cousin, who will be able to afford some of these other more expensive, why should I say that, but other alternative therapies. I'm very happy are also being developed for sure, without a doubt. But I want to make sure that our agents are able to reach more patients, because there are millions of patients who have sickle cell disease, and 100 milligrams already is showing really great efficacy, and we continue to work. Okay, so 601 is also safe, as I've shown you, increased hemoglobin. The doses tested to date, we know that it inhibits sickling and the downstream sequelae, and we also know that it has the potential to impact not just increasing hemoglobin, but some of the other pathologies like VOC and pain. And we're currently in a clinical study, full speed, developing it, so that we can patients can have access to it, hopefully in the future. And with that, I'd like to say thank you, and I'll take any other questions that you may have.
Okay, Dr. Love, has sickle cell blood been used as a treatment plan for HIV patients? If so, how and why are sickle cell beneficial for the HIV community?
Nadine, and it may have been a little bit confusing the way I described it. Sickle cell would not be a good treatment for HIV. The analogy I was trying to make with HIV is that in HIV, the problem is the human immunodeficiency virus. And we were treating what the problems caused by the virus and not the virus. So we were improving things, but we weren't really what Kobe just said. We weren't pharmacologically curing those patients. So people still would die of HIV, but we were helping by treating the downstream consequence. So by analogy, what I was saying is that by providing vaccinations, penicillin, we were changing the outcomes of sickle cell disease in a positive way, but we weren't treating the fundamental problem, which in the case of sickle cell disease is not the virus. The problem here is polymerization. So we've been trying to basically, by analogy, treat the fundamental problem as we did in HIV, as we've done in cystic fibrosis, now in sickle cell disease, because we think if you treat the fundamental problem, our goal is to convert sickle cell disease into non-sickle cell. If the sickling goes away, we think the outcomes could be dramatic. And we needed to do that with a dose that people hopefully would have very little to no side effects from. And that's the goal with 601. I'll just mention one other thing that's important. When I was running the company, we were spending a lot of money on sickle cell disease. We were spending hundreds of millions of dollars a year. And many of our investors would say, why don't you guys move on? Voxelotor looks really good. And people like me and Kobe were like, we can do better. So we were spending about $20 million a year in the lab every year making new molecules. And Kobe, maybe you could tell people how many molecules we made to get from Voxelotor, which was an amazing advance, to 601. I mean, it was how many?
Hundreds of thousands of molecules. I mean, so actually not 601, but it's 222,601. So we turn them around. We spend a lot of money, but I'll tell you this, when the company started, we were in one small room, and even then we were very productive. There's one thing we know how to do, when you put the right team together and you have a leader like Ted, and you've got a relationship, you are motivated, right, to do better for your own folk. So we crank through the compounds like nobody's business, and that's why we are where we are today.
Okay, so I just want to say this too. We don't have to. I'm sorry. We don't have to close at like 1 o'clock. I mean, we always leave open that extra half hour. If you gentlemen have that time, I really appreciate it. I got one other question, and then Wanda, did you? We'll go to you.
I have a question.
Okay. Let me ask this one question, then we'll go to you. In the best case scenario, when could 601 be available to patients?
That's a tricky question for me because I'm no longer part of the company. Pfizer acquired the company, and I am not directly involved. And Kobe is not doing the clinical trials either. So I think, realistically, it will take at least several more years
Some
to
time.
do all the studies, because drug approval by the FDA is a very high bar, and it should be a very high bar. Before we put a drug in physicians' hands, we ought to have a lot of confidence that that drug not only works, but that it's safe. And Pfizer needs time to do all of that work. And one of the things, Nadina, that's important is to also have people be on the drug for some period
Right.
to know that it's safe.
Absolutely.
So if you treat somebody for one
Absolutely.
day, you don't know it's safe long term.
Yeah.
So
No.
we need to generate long-term data too. So it will be years before 601 is available, but Kobe and I are just phenomenally excited that we think we, potentially could have solved HIV. I mean, like we've done in HIV and like we've done in CF, we potentially, and potential is an important word here, we could potentially have fundamentally the solution for sickle cell disease.
Cool. Okay. Wanda?
Okay, two questions. One, the name change from Oxbryta to Veloxor, I was a little bit confused or thought I missed the explanation for
Yes.
that. And the other question was, now that GBT has been purchased by Pfizer, how are things different?
Okay, I can answer the first one real easily, and the second one I'll try to my best.
Well, I hope you can answer the first one real, because I asked you to name it after Kareem, but you go ahead.
So drugs, therapies have two names. One name is called the generic name. And even when the drug goes generic and the company that invented the drug is no longer selling it, that name will continue to live. So one day somebody else other than Pfizer will sell voxelotor. They can't call it Oxbryta because Oxbryta is a proprietary name that belongs to now Pfizer. It used to belong to GBT. So it's the same molecule, but it's the proprietary name. So drugs always have two names. One is a generic name that anybody can use in the future, and one is the proprietary name that belongs to the drug when it's only being sold by one company that invented it.
Okay, so I just have a question. How did you come up with Oxbryta then? I mean, who is that?
Naming drugs, I got to tell you, it's a very big deal, because number one, different names can mean different things in different cultures and different societies around the world. One of the great naming eras that's kind of funny is the Chevy Nova was a great name in the US, but they noticed that the cars were selling very poorly in South America because Nova means no go.
Nova.
In those environments.
Nova means no go.
So that's not a good name for a car.
I love it.
So when we did our naming, we actually got names from a professional company. They tested these names around the world to make sure that there was no a negative association anywhere in the world that we could find. So naming a therapy that you're with a name that you're going to use around the world is very complicated. And actually you spend millions of dollars trying to make sure you get it right. You don't want to
That's why if you'd named it Kareem, you wouldn't have spent millions of dollars. Everybody would know what Kareem meant. That's right. That's my boy. That's all I gotta say. Now, to Wanda's next question.
Changes since GBT was purchased by Pfizer.
Well, let me just cite a few that are obvious. One is I don't work for the company. I'm not associated with the effort anymore. Pfizer did, however, absorb a lot of our great employees, like Kobe. So a lot of the people who worked for GBT have now become part of Pfizer. And so in some of those ways, things are not that different. Couple of positive things that I'll cite. Pfizer is much bigger than GBT, obviously, and they have an infrastructure all around the world. So they can much more readily make Oxbryta available in these countries all over the world. GBT was trying to build that, but we were building it in a disciplined way because we never turned a profit. We lost money every year I ran the company. I raised $1.5 billion to keep the company going, and I probably would have had to raise even more. But the Pfizer acquisition means that now the infrastructure and the capacity to make the drug available all around the world is instant. The other thing that's really, really positive is that Pfizer announced a program under Albert, the CEO, about 3 years ago to make their drugs available in the 45 poorest countries in the world at their cost. So they don't make any money, but if they can make the drug really cheaply, they can make it available in these 45 countries in the world at their cost. GBT couldn't afford to do that, and Pfizer can. So there are a number of positives about this, and maybe it's even a positive that I'm not there anymore, but I'm not there anymore.
No, that's not a positive for
I
us.
doubt it. I doubt it.
You made a very, very big difference. You were the first pharmaceutical company that I've ever dealt with related to sickle cell that really felt like you had a heart for the people living with sickle cell. And that was, just an enormous plus. Just your bringing people together with sickle cell, ask them, what was it like living with sickle cell? No one else had ever done that. So kudos to you.
Well, that's the way it should be. That's the way it should be for every disease. And what I tried to bring to sickle cell disease was the humanity, the personal concern about every individual that frankly everybody should have for every patient. Sickle cell was being under empathized with. It was being under funded. It was being under everything. So
it was under everything. It was under everything. That's all I got.
Under.
Yeah, it was under. You don't even need to go there. It's under.
Right.
We're trying to solve some of those issues.
Yes, I know you are.
I can add a little more flavor to what's happening in Pfizer because I'm still at Pfizer. So as Ted said, I think they have propensity to reach more patients. 100%. That's important. But some of us have also stayed because cultures are a bit different sometimes. Big company culture, they have many assets, right? So
yes,
and it's different. Like I said, family with sickle cell, I've been very close to it. I told my mother, this is probably the most important thing I'll have to do in my career. And Ted, people like Ted who are my, okay, you have a career still, stay, manage, make sure 601 gets out properly. And importantly, bring the culture that Wanda was just speaking to, how we've addressed sickle cell disease. As Ted said, that's how it should be with any other disease. But the idea is to bring that culture, some of that culture to Pfizer, which is why some of us are still here at Pfizer, trying to reintroduce new ideas. And I'll be honest with you, you've actually changed the way some of the ways in which they operate and how they think. They have the opportunity, Pfizer, because of COVID, to think differently about how they do drug development, to go very quickly. Because the point is, you don't have all the time in the world. People are suffering, and you gotta step on it, right? So I'll never forget it.
It's a privilege when you step on it.
Right? Gotta pick this up.
I'll never forget it because the first talk I gave was on Oxbryta and how it was discovered when we were Pfizer. And I distinctively remember someone saying, "Oh yeah, we developed the vaccine at light speed," and I kept hearing this term light speed, and I thought, wait. So I raised my hand. I said, "What's light speed?" They're like, "Well, light speed is when there is a huge need and you got to go. You have to step on it and go." And I thought, well, at GBT, there's no non-light speed. We're always we're careful, we're always light speed because we understood, that the people are waiting, So now, some of us we have titles called pilots in command, and,
I love it.
we influence the process when we can and say, hey, light speed mentality, right? Where can we cut costs? Where can we do some things at risk safely so that we can quickly get these important agents out, right? So I just want to add a bit of that.
We've been waiting. We're all waiting. This community has been waiting for eons. Okay. So I'm going to just give you 2 more questions and then we're going to call it. Are you working with any socialist on addressing the social issues that revolve around sickle cell community?
I was sociologist.
Oh, I'm sorry. Are you working with any sociologists on addressing the social problems with that revolve around the sickle cell community?
Maybe Ted can take the first part, because as part of GBT, we had several initiatives to not only pay attention to drug discovery, which led to the discovery of Oxbryta, but we immersed ourselves into the community. And, it's a part of why we're here, right? Meeting Adina, we recognize that sickle cell is not just some disease that you just develop a drug and walk away and say, hey guys, go and take a pill, right? There are multiple social issues that are associated with it. And at the heart of it really is the fact that the disease has been around for hundreds of years, but without significant attention, right? Which is why Ted's approach to sickle cell was very different. Don't just make the drug, understand what the community needs so that you can. And around that, Ted built infrastructure to, I hope, that's reflective of all the good things that you guys have talked about and where we are today with sickle cell. And Pfizer continues to have those initiatives in place, not just for sickle cell, but for every other indication that they go after. The only difference here is that we are very passionate about sickle cell. So as part of GBT and becoming part of Pfizer, we make sure that they continue some of these efforts, to the degree that we can influence the process.
Yes. And you just said it, the key word there, influence. We need to influence that passion in Pfizer, because I know Pfizer is a big organization and they got a lot of areas that they focus on. That's and right. They just need to have some more folks focusing on sickle cell community. Now, this last question, how can we keep Pfizer transparent in regards to evolving the needs of the sickle cell community with you no longer being the CEO?
Well, I mean, what I would say is, it's a continuous process. Rome wasn't built in a day. The progress, I mean, I'm a kid that grew up in the Jim Crow South. I grew up in Alabama. And we've made some progress, but we still have a long way to go. And so I think that anytime you are trying to change something big in a fundamental way, you've got to realize that it's not a sprint, it's a marathon. And I think, here we just have to stay vigilant, stay focused, and we'll get the progress, but it will take time potentially.
I like that. It's not a sprint, it's a marathon. I just wrote that down. That's great. Okay. Pat has a question. She has her hand up. Pat?
So I don't really have a question. I just want to do a shout out to Ted and Kobe for the wonderful session. Really wished more people had done a dive into it, because it's phenomenal. You guys shared a lot of information. You shared the whys, the hows, the whos, the whens, the wheres, and it gives us a lens into what things we need to be doing out in the community to make a difference for people living with sickle cell disease. And then even more importantly, my praises go out to the organization that actually organized this. Nadina, you guys are awesome. And thank you for what you do in the community, and stay encouraged. The best is yet to come, for not just us working hard in this community, but for people living and the people that surround them. So So Ted, again, it was nice, wonderful seeing a person who looked like me having such an effect on what was happening in our community, because so often we're sitting on the bleachers cheering it on, but we are not participating. We don't have a spot. We don't have a voice. And so I just thank you guys for what you did for sickle cell. I've been around a long time, you know, not telling my age, but I've been around a long time. As a young person, I got tricked into sickle cell because I didn't even know what sickle cell was. But I can tell you that being a part of the sickle cell community has made me a better person and has made me really be able to appreciate what value we as healthcare providers have within this community. So thank you again for what you do and how you do it, and when you and where you did it, because it really gave us a presence. I just wish we could infiltrate all these other groups who are now in the sickle cell arena, where the money is drying up very quickly for us, to understand the significance of sickle cell and what a difference they could make for people who live in this community of color that is disproportionately really having a presence in science.
Pat, it's great to hear your voice, number one. And number two, I'm sure Kobe will agree. It takes a village to drive the kind of change that we're all expecting and hoping for in sickle cell disease. And we've just been thrilled and so rewarded to be part of it. And that's what we know. We're just part of it. It's an ecosystem, and it takes a village. And just so appreciative of your work and the other work of other people in this community who've taken us to where we are and will take us to where we know we're going to get.
Ms. Nadina, can I ask one last question?
Yeah, because I couldn't ask all your questions, but you go ahead, Christian. You got one last question, sir.
Okay. I want to first say that your prolific presentation and your position in the sickle cell community is very honorable. I think when we consider how we can change the narrative, I think that this is, you know, what comes to mind moving forward. You mentioned you fundraised $1.5 billion for GPT. That's huge. So my question is, in response to that, you know, $1.5 billion, that's not easy. That's unheard of for the grand majority of our community. So I would say, when you were raising the 1.5 billion, did you raise that with the intent to sell GPT? And if so, can you touch on that a little bit? And if it wasn't the case, you know, the motivating factor and maybe even some of the method and process. Because one of the things that we are learning is what a lot of the community benefit organizations that are serving the sickle cell community on a grassroots level is fundraising is a challenge, and it sometimes arrests development.
Yeah.
So I think the process and the method, I mean, even if it's not 1.5 billion, you know, even some of these community benefit organizations, 1.5 million would be, it would take the organization to a sustainable level. So I would just want to if you had a moment just to kind of touch on the process and method, and then also what motivating factor with raising that 1.5 billion.
Yeah. So I'll be real quick about this. Our goal was to build a great company, not to build a company to sell. And in fact, I think it's a real flaw to focus on building a company to sell. What you focus on is build a great company that becomes increasingly valuable because you're creating a lot of value by making therapies which are going to transform the lives of patients. That's our business. Now, if you build a great company, it is very possible that somebody big will come along and say, I want your company. And if they offer enough money, because these are public companies, you can't really say no. Now, if they're offering you less than you think the company is worth, and the board thinks the company is worth, you can say no. But there is a number where you really cannot say no, because it's not your company. You're really stewards of the shareholders that own the company. When I was raising money, just to be very clear, the people giving me money wanted more money in return. So these people would give me $1 and they'd say, okay, I'm entrusting you are going to come back and this is going to be $10 one day. It wasn't philanthropy. I do a lot of raising money for philanthropy. I helped start Life Science Care here in the Bay Area. We try, where our goal is to raise and give away $10 million to charity every year. These are different people. The people that I was raising money from, they want to make more money. These are, TIA CREF, the Teachers Retirement Association, Fidelity, Wellington. These are people that you give your money to, and you expect them to return you more money. So the money I raised was money from investors that had confidence that I would turn their dollar into something much greater than $1. And coming back to the Pfizer acquisition, they were very happy with the Pfizer acquisition because they suddenly, there were people buying our stock for $25 within a year of the acquisition, and they suddenly got $68.50 for it. So they were like, "Go, Ted, you made me a lot of money." So that's why this ecosystem is really important, and that's what I was trying to do. I had to get out there and convince investors that if you give me your money, I'm going to make you more money. Those people really are not emotionally concerned with sickle cell disease. They're emotionally concerned with making more money, and that's one of the reasons that the acquisition also made a lot of sense, because it inspired a lot of investors to change their position, because there'd been a lot of rhetoric. You can't make money in sickle cell disease, and so nobody would invest in sickle cell disease. So GBT became this shining example of you can make a lot of money in sickle cell disease if you do a great job.
That's right.
And we did a great job, and we did make a lot of money for our investors. But more importantly, I think we could change the lives of people with sickle cell disease globally.
Brother Love.
I got a question. So can we get the plan on how we can raise that kind of money, or how we can, hey, that's all I need to know. How can I help me to become sustainable, help this organization become sustainable?
That's right. That's right.
That's it. That's it. That's my question.
Yeah,
like,
Nadina,
hey, I want the blueprint or the platform or the
PowerPoint presentation.
Whatever it is, man, we got to share that. So yeah, hey,
what's the formula, brother?
We're struggling, but we're still out here, and we will continue because we recognize that this community needs us. They need all the community-based organizations that are available, because there are so few, and you still got the adults dropping off the side of the cliff. So, hey.
So can I just add one other thing? So that was one of the reasons. That was one of the reasons we were working with Barbara Lee and Cory Booker and others to try to get the Sickle Cell Treatment Act passed, which would appropriate $535 million from our federal government that we are giving money in our taxes to sickle cell disease. And that's not a lot of money. It sounds like a lot of money, but it's not a lot of money when you think about the number of people suffering from sickle cell disease in this country. So I'm still committed to trying to get the government, which is by far the richest institution in the world, much richer than Pfizer, to put out the $535 million a year to build good sickle cell treatment centers, to help fund the CBOs, Nadina, that you referred to help fund the ecosystem to help sickle cell disease. So, GBT was a great thing, but we need to do a lot more. And I think the Sickle Cell Treatment Act is something that we need to pass, and I'm going to do everything I can to get it passed.
Okay, well, I have to say, just like I told you at my last speaking at GBT, that GBT was the best, has been the best and the most supportive of our organization since it began. And since we all wept in the same room together, it was a great moment for me, and that will always be a memory for me. And that's why you guys have just showed up for me so much, and I really appreciate you. And I want us to continue our relationship and speak on regular basis, and just keep up with what things are going, what things are happening, and what's developing, and how we're moving forward.